NASA is not just trying to land on the moon again, it is trying to build the first real off-world base at the lunar South Pole, using cargo systems, power, robots, habitats, and local resources. And if Artemis works, the moon stops being just a destination and becomes the place where humanity learns how to live beyond Earth. The first thing you need to drop is the fantasy that NASA will build a moon base by landing one giant habitat and calling it done. That is not how a real base works. A real base is a system that keeps moving people, cargo, power units, spare parts, vehicles, data links, and life support equipment into a place that is extremely hard to survive in. If that flow breaks, the base is not a base anymore. It is just stranded hardware. That is why the real story is not one big landing. The real story is whether NASA can build a repeatable pipeline to the lunar surface, and that's exactly why the numbers matter more than the image in your head. In the early phase, the amount of payload reaching the moon is only a few thousand kilograms. Later, the plan scales toward about 60,000 kilograms, and then much higher toward about 150,000 kilograms. In pounds, that is roughly moving from a few tons to around 132,000 pounds, and then to about 330,000 pounds. That is the real growth curve. It tells you whether the architecture is becoming useful or not. A base is not created by a famous landing. A base is created when the flow of mass becomes dependable. So what matters more, one successful mission, or the ability to keep doing missions on schedule? For a moon base, the answer is the schedule. A single landing can prove you reach the surface. It cannot prove you can live there, maintain systems there, recover from failures there, or expand there. NASA's phase planning makes that very clear. The path moves from early tests and a first crewed moonbase mission into initial infrastructure, then into regular crewed missions, and finally toward continuous crew presence. That shift is everything. It means Artemis is trying to move from isolated expeditions to repeat operations, and repeat operations are what make the difference between exploration and infrastructure. If astronauts arrive once, do some work and leave, that is still a mission. If crews keep returning, cargo keeps arriving, systems can be repaired, broken hardware can be replaced, and the outpost keeps getting stronger instead of starting over each time, that is something else. That is the beginning of a real base. On the moon, reliability is not just good engineering, it is survival. This is also why the whole idea starts looking less like Apollo and more like logistics. When you look at the phased launch and landing counts, the picture changes fast. NASA's planning shows something closer to a campaign than a single historic event. You're looking at dozens of launches, dozens of landings, and a steady increase in cargo capability, including commercial delivery systems that grow towards several metric tons at a time. Even if those exact figures change later, the message stays the same. Artemis is not built around one heroic descent. It is built around repeated transport, repeated landing, repeated support, and repeated recovery. That should completely change the way you think about the word base. Most people hear that word and think about a structure. NASA is really talking about a transport and support system that becomes strong enough to keep a structure alive. That is a much harsher definition, but it is the correct one. The habitat matters, of course, but the habitat is only one piece. If you cannot keep supplying it, powering it, servicing it, and connecting it to other systems, it is not a functioning outpost. It is just a box on the moon. Then there is another shift that matters just as much. Early missions can survive by carrying most of what they need. A single lander can bring its own power, its own communications, its own navigation tools, and its own consumables. That works for short missions. It does not work for growth. Once NASA starts talking about long-term expansion, it starts talking about shared systems, shared power, shared logistics, shared communications, shared navigation, shared mobility. That is a major change in the architecture, because now the goal is no longer to keep one mission alive in isolation. The goal is to make multiple missions depend on the same infrastructure. And once that happens, you're not just running missions anymore. You're building services. One power system may support several assets. One communication layer may connect habitats, landers, rovers, and Earth. One navigation system may guide both astronauts and robots across the same terrain. One cargo handling setup may support repeated unloading and redistribution on the surface. That sounds technical, but it is actually the clearest sign that NASA is trying to build public infrastructure on another world. Why is that such a big deal? Because self-contained missions do not scale well. Every vehicle has to bring almost everything for itself. Every mission repeats the same burden. Shared systems change that. They let later missions plug into something that is already there, that reduces waste, reduces duplication, and makes growth possible. It also creates interdependence, which means failures become more serious. If shared power goes down, or shared comms fail, or a shared cargo system breaks, more than one mission can be affected. So the architecture becomes more capable, but it also has to become more reliable. That is why the boring parts are actually the deciding parts. Spare parts storage, cargo transfer, surface maintenance, utility connections, timing, schedules, redundancy, repair plans, these are not side details, these are the foundation. People usually focus on launch day because launch day is dramatic, but a moon base will live or die on ordinary days, days when cargo has to be unloaded, days when something breaks and has to be fixed, days when a power unit has to keep working in bad conditions, days when no one gets a second chance because the moon has no backup system waiting nearby. So the hard truth at the center of Artemis is very simple. NASA is not trying to place one permanent object on the moon. NASA is trying to create a working flow of mass, equipment, energy, information, and crew movement that can survive long enough to support growth. That is what turns a landing zone into an outpost. Then it turns the outpost into infrastructure. Then only much later does it start to look like the kind of base people picture in their heads. And that leads straight to the real stakes. The Artemis Moon base will not be built by one spectacular success. It will be built by repeated success in things most people barely notice. Delivering cargo on time, keeping systems alive between missions, expanding surface capability without losing control of complexity, connecting each new asset into a larger support network. That is how ports are built. That is how remote stations are built. That is how any dangerous place becomes usable. On the moon, the rule is even stricter, because every weak link can become fatal. So the habitat is not the base. The first landing is not the base. Even the first crewed stay is not the base. The base is the network that keeps all of those things working together. And once you see it that way, the whole Artemis program becomes much more serious. This is not just about getting back to the moon. It is about proving that humans can keep a complex system alive there. And that raises the next problem immediately. Even with the right architecture, the base still needs the right location. NASA is not going to the South Pole because it sounds dramatic. It is going there because the wrong place would make long-term survival much harder from the start. So why would NASA choose one of the hardest places on the moon to build anything at all? Because the easy places are not the useful places. That is the first thing you need to understand about the lunar South Pole. NASA is not going there because it sounds dramatic. It is going there because that region may offer the one combination that matters most for a long-term outpost. Better access to light in some areas, and access to frozen volatiles in others, especially water ice. NASA's moon base planning makes the logic very clear. The South Pole has strategic, scientific, and economic value, even if that means giving up short-term convenience. So NASA is deliberately choosing the harder site because it may be the only kind of site that can support something permanent. That is a major break from the way most people think about lunar missions. If the goal was only to land, do some science and leave, NASA could favour simpler terrain and easier operations. But Artemis is not aiming for the simplest place to visit once. It is aiming for a place that might keep paying back over time. Water matters for drinking, for oxygen, and eventually for fuel production. Lighting matters for power. Science matters because the poles preserve conditions that can tell us things about the moon's history that other places cannot. So the South Pole wins for one reason. It gives NASA a chance to build something that can last. even though it makes almost every engineering problem harder. Then you hit the next problem immediately. The light near the pole is not normal daylight. Near the moon's equator, the pattern is easier to understand. You get about 2 weeks of sunlight, then about 2 weeks of darkness. That is already hard, but at least it is a clear cycle. Near the poles, the geometry changes. The sun stays very low on the horizon. That sounds useful at first because some high areas can get light for long periods, but the reality is much more difficult. Low-angle sunlight creates long shadows, sharp contrast, and constant terrain masking. One ridge can block light from an area that looks open on a simple map. One crater wall can leave equipment cold and dark for a very long time. That means solar power at the pole is not a simple matter of putting out panels and waiting. The panels have to deal with shallow sunlight, changing shadow patterns, and terrain that can cut power production badly, even when the sun is technically above the horizon. NASA's planning warns about this directly. The low sun angle creates strong shadowing, makes solar electricity harder to generate, and forces systems to survive long periods of cold and darkness. So the South Pole is not a bright, stable work site. It is a place where light itself becomes part of the engineering problem. And that is where the tension gets worse. The same geometry that may help some peaks get more light also creates areas that are among the coldest places anywhere in the inner solar system. The moon already has extreme temperatures. Near the equator, surface temperatures can rise above 121 degrees Celsius, or about 250 degrees Fahrenheit, in sunlight, then fall to around minus 133 degrees Celsius, or about minus 208 degrees Fahrenheit at night. But in permanently shadowed craters near the poles, the situation becomes much more severe. Measurements have found temperatures below minus 246 degrees Celsius, colder than minus 410 degrees Fahrenheit. That is not just a cold weather problem, that is a hardware survival problem. Metals change behavior, batteries struggle, lubricants can fail. Thermal control becomes one of the main battles for survival, but this is exactly where the South Pole becomes so important. Those extreme cold traps may also preserve water ice. NASA's ice analysis points to the highest ice concentrations in places colder than about 75 Kelvin, which is roughly minus 198 degrees Celsius, or about minus 325 degrees Fahrenheit. So the colder the terrain gets, the more valuable it may become. The same environment that threatens your systems may also hold the resource that makes the whole outpost possible. That is the real trade. NASA is not just picking a difficult place. NASA is picking a place where the danger and the opportunity are directly tied together. If you stay in the easier terrain, you may lose access to the resources that make long-term survival realistic. If you go into the colder, harder terrain, you gain access to those resources. But now every machine and every mission has to survive in a much more hostile environment. That is why the South Pole is not just a destination. It is a test of whether the benefits are worth the operational pain. And the terrain makes that pain very real. The South Polar region is not just one smooth, flat plain. NASA describes it as a region of high mountains, deep craters, and many different terrain types packed together. That means Artemis is targeting a version of the moon that Apollo never had to deal with. Apollo worked mostly in sunlit equatorial regions where the geometry was simpler and the terrain was less dominated by deep shadow boundaries. Artemis is going into a landscape where a slope is not just a slope. A slope can affect power access, communication lines, navigation safety, thermal survival, and even whether a crew can get back along the same route. That changes how you think about movement on the surface. A rover cannot just drive from point A to point B and assume that the space in between is manageable. It may have to deal with sharp transitions between light and darkness, broken ground, crater rims, loose regolith, and areas where line of sight to the habitat or relay assets disappears. If a crewed vehicle or robot moves into the wrong low area, it may lose sunlight, lose temperature margin, and lose communication support at the same time. So mobility at the South Pole is not only about distance, it is about terrain, timing, and geometry all working against you at once. That is why site selection is already a serious scientific and engineering process. not a ceremonial choice. NASA refined Artemis' 3 candidate landing regions near the South Pole into 9 areas, including places like Peak near Cabus B, Haworth, Malapert Massif, Mons Mouton, and the Nobile Rim region. That detail matters because it shows there is no single perfect location waiting for NASA to claim it. There is only a trade space. One area may have better light, another may have better access to volatile-rich terrain, another may have safer slopes, another may offer better line of sight for communications, another may have stronger science value, so the base does not start with one obvious dot on a map. It starts with layered decisions, lighting maps, slope maps, hazard maps, communication geometry, access to shadowed regions, access to possible ice deposits, safe landing conditions, surface traffic routes. All of that has to be weighed together. One bad ridgeline can reduce power options. One badly chosen landing zone can make cargo delivery harder for years. One strong elevated site can become the anchor point for power, communications, and future expansion. That is why the moon base will not be born from a symbolic location. It will be born from a brutal location analysis. And once you see that, the South Pole stops looking like a dramatic destination and starts looking like a narrow answer to a hard question. NASA is going there because easier terrain may not support permanence. The poles may offer the light windows, the ice, and the science that make a base worth building at all. But the price is that everything becomes harder at the same time. Power, landing, mobility, communications, thermal control, and site planning. Artemis is not choosing comfort, it is choosing leverage, and that leads straight into the next major problem. Even if NASA picks the right region, even if the map is good, even if the South Pole offers the resources the program needs, none of that matters unless Earth can actually throw enough mass toward the Moon to begin building the system in the first place. The moon base does not begin on the Moon. It begins on Earth with a very simple limit. How much mass can you actually throw out of Earth's gravity well and send toward deep space? That is the first hard gate. Before you talk about habitats, power systems, rovers, landing pads, or ice mining, you need launch capacity. If Earth cannot send enough hardware outward, then nothing else in the plan matters. That is where NASA's Space Launch System comes in. It is the brute force part of Artemis. The Block 1 version stands about 98 meters tall, or 322 feet. Fueled, it weighs about 5.75 million pounds. At liftoff, it produces about 8.8 million pounds of thrust, which is even more than Saturn V. NASA says it can send more than 27 metric tons, about 59,500 pounds, beyond the Moon. Those numbers are not just for posters, they define the starting economy of the entire base. Every pressure vessel, every section of habitat wall, every suit part, every life support component, every box of tools, every spare pump, every connector, every battery module starts with lift from Earth. On the Moon, mass is survival, but before mass becomes survival, it is a launch problem. That is why the rocket is not separate from the base story. It is the first physical piece of the base, because without launch there is no cargo flow, no crew flow, and no build-up at all. Then there is the next reality check. Getting hardware out there is only half the problem. You also have to get people there and bring them back alive. That is why Orion matters so much. Orion is not the machine that builds the base directly. It is the machine that keeps the crew from becoming stranded at the edge of cislunar space. Its job is not glamorous. Its job is survival. It has to carry astronauts far from Earth, support them through deep space transit, and then survive a return that is much harsher than a normal trip back from low Earth orbit. Artemis 1 came back at about 39,560 kilometers per hour, or around 24,581 miles per hour, about Mach 32. That is an extreme return environment. The heating is harsher, the re-entry is harsher. The margin for error is smaller. So when people picture a moon base and focus only on the surface, they miss something important. Orion is the long-haul crew transport and the emergency path home. It is the ferry to the larger system. It is also the proof that surface expansion does not trap astronauts farther from Earth than any human settlement has ever been. That is why Orion matters. A base is not real if the transport system that connects it to Earth is weak. Before the Moon becomes a place where crews can stay longer, the route back has to be solid. But even that still does not give you the full picture, because Artemis is not one rocket and one capsule doing everything. This is one of the biggest differences between Artemis and Apollo. Apollo looked cleaner from the outside because one national system dominated the whole mission profile. Artemis is much more mixed. Gateway's first two elements, PPE and Halo, are planned to launch together on a commercial Falcon Heavy ahead of Artemis 4. The human landing system is commercial. Robotic lunar cargo through CLPS is commercial. NASA still brings the government's Super Heavy launch vehicle and the government crew spacecraft, but the larger campaign depends on a combination of public and private systems working together. That matters because it changes how the moon base is assembled. This is not one giant government stack flying in one straight line from Earth to the lunar surface. It is a distributed architecture. Government Super Heavy launch, commercial heavy launch, government crew transport, commercial landers, commercial robotic delivery, orbital infrastructure, surface systems, multiple providers, multiple vehicles, multiple mission types. That arrangement is more complex, but it also makes more sense for a long build-out. A base does not grow well if only one vehicle can do one job. It grows better when different vehicles handle different parts of the flow. That also means the public version of the story can be misleading. People wait for one iconic mission and assume the program is stalled if that single moment has not happened yet. But current NASA material shows something more phased and more procedural. As of 2026, Artemis 3 material still emphasizes low Earth orbit demonstrations for commercial lander, rendezvous, and docking capability. At the same time, NASA's budget material for fiscal year 2027 points toward lunar South Pole surface exploration in 2028, and then roughly one lunar mission per year after that. That tells you something important. NASA is still working through the stage where systems are being proven, integrated, and de-risked before the surface campaign becomes more routine. That does not make the effort smaller. It makes it more honest. Building a moon base is not one delayed scene waiting for the camera. It is a chain of hardware demonstrations, docking tests, landing tests, cargo development, and operations planning that has to become boring before the base can become real. This is the transition from demo culture to operating culture. In demo culture, the point is to prove you can do a thing once. In operating culture, the point is to keep doing the thing on schedule, with maintenance, with upgrades, and with room for failure recovery. That second stage is where bases come from, and this brings you to the hardest launch truth in the entire Artemis story. Every kilogram on the moon is expensive twice. First you have to launch it off Earth, then you have to land it safely on the moon, and not just anywhere, but in difficult polar terrain. That means even small hardware choices matter. A heavier structure is not just heavier at liftoff, it is also harder to land, harder to place, and harder to integrate into the surface layout. So when NASA talks about local resource use, increasing cargo capability, and shared infrastructure, that is not optional future improvement. It is the only way the economics can eventually make sense. Earth is not going to make the moon base cheap. Earth is only going to provide the initial push. Launch from Kennedy buys the first habitats, the first cargo, the first power systems, the first robots, the first surface mobility, and the first crew access. After that, the architecture has to get smarter. It has to scale cargo delivery, it has to reuse systems where possible, it has to share utilities, and eventually it has to get some value back from local lunar resources, because if every single kilogram always has to come from Earth, then the base stays limited, fragile, and painfully expensive. That is the real pivot point. A lunar outpost begins as an expedition supplied from Earth. A true base begins when Earth launch buys just enough capability for the moon and to start reducing some of its own logistical burden. Not all of it, not even most of it at first, but enough to change the trend, enough to make the next mission build on the last one instead of repeating it from scratch. So the launch pad at Kennedy is not just where missions begin, it is where the whole moon base problem begins. Can Earth launch enough mass? Can it launch it often enough? Can the crew system survive the trip? Can multiple vehicles from multiple providers work as one architecture? Can the program move from isolated demonstrations to dependable operations? Until those answers become yes, the moon base is still only a plan. And once those answers do start becoming yes, the next question gets even harder. Launching mass toward the moon is one thing. Managing traffic, crews, vehicles, and logistics around the moon over and over is another. That is where the surface campaign stops being just a launch problem and starts needing an orbital scaffold above it. So if the base is on the moon, why does NASA also need a base above the moon? Because repeat operations are harder than a single landing. Gateway is not the moon base itself, but it is the orbital system that makes the surface campaign easier to repeat, easier to manage, and easier to expand. NASA describes Gateway as a multi-purpose outpost that supports lunar surface missions, science in lunar orbit, and future missions deeper into space. That already tells you what role it plays. It is not there for symbolism. It is there because sending every crew and every lander straight from Earth to the surface and back again makes the whole architecture harder to scale. Gateway changes that by creating a staging point in lunar space. Instead of treating every mission like a fresh one-off attempt, NASA can build a system where crew vehicles, landers, cargo, and support modules meet in orbit and work through a more repeatable sequence. That is why the first two Gateway elements, PPE and Halo, matter so much. They are not just hardware pieces, they are the beginning of a permanent orbital layer above the surface campaign. And the fact that they will launch together and then spend about a year getting into lunar orbit tells you something important. Gateway is not an afterthought. It is not a side mission. NASA is treating it as infrastructure. Then you get to the next question. If Gateway is so important, why put it in such an unusual orbit? Because ordinary lunar orbit is not good enough for what NASA wants. Gateway is planned for a near-rectilinear halo orbit, or NRHO. That orbit has a period of about 6.5 days. It sounds very specialized because it is. NASA did not choose it because it looks elegant on a diagram. NASA chose it because the orbit solves practical mission problems. It gives Gateway a stable and useful path around the moon that works well for future Artemis operations. That matters more than it sounds. Orbit is not just a path. Orbit decides fuel demand, transfer opportunities, communication geometry, and how predictable rendezvous operations will be. If your orbital outpost comes back to the right place at the right time on a regular cycle, then you reduce the amount of propellant missions need, make transfers easier to plan, and open up more options for landing and return. If you pick the wrong orbit, the penalties do not always show up in one dramatic failure. They show up in constant extra mass, constant extra complexity, and constant extra mission constraints. Over time, that can quietly damage the whole campaign. So Gateway's orbit is part of the base story in a very direct way. A bad surface architecture can kill a moon base, but a bad orbital architecture can do it too. It can make every mission more expensive, every transfer harder, and every schedule more fragile. That is why this strange orbit matters. It is one of those hidden decisions that either keeps the system efficient or slowly drains it. Then there is another step people often miss. Gateway is not just a passive stopping point. It is not just a place where astronauts wait around. That becomes clear when you look at PPE, the power and propulsion element. PPE is designed to provide about 60 kilowatts of solar electric power, along with communications, attitude control, and orbit maintenance. NASA also said engineers successfully powered the element on the ground in 2025. 60 kilowatts is not a city power system, but for a deep space outpost it is a serious amount of utility capability. And that changes what Gateway can actually do. With that much power and propulsion support, Gateway becomes an active piece of infrastructure. It can support avionics, communications links, visiting vehicles, and the work needed to maintain its orbit. It is not just a module hanging in space. It's a functioning node in cislunar operations. It gives NASA a platform that can help manage traffic, support missions, and remain useful between crew visits. That is a big step, because the moment an orbital outpost can support itself as a working system, it starts becoming part of the long-term backbone instead of just a temporary platform. Then you add Halo, and the orbital system starts feeling even more complete. Halo provides the first pressurized living and working volume for astronauts. After that, NASA and ESA describe Lunar IHAB as the next habitation module. ESA's Lunar View and Esprit add more capability, especially for refueling and communications. Then you have JAXA contributing to Gateway and also to the pressurized surface rover. The UAE is contributing the airlock module, with that role formalized in 2024. Once you lay all of that out, Gateway stops looking like one country's project with a few guests attached. It starts looking like multinational infrastructure from the beginning. That matters because deep space systems become more durable when multiple partners are part of the architecture. Because it creates a broader industrial and operational base behind the hardware. More modules, more providers, more shared responsibilities, more experience flowing into the same system. The moon-based story is not only about one country returning to the moon, it is about whether multiple countries and companies can actually help build a shared operating environment beyond Earth. And this is where the stakes rise again. Once you have Orion bringing crew toward lunar space, Gateway sitting in orbit as a staging node, and landers travelling between orbit and the surface, the moon stops being a single arrival event. It starts behaving like a transportation network. Crew transfers, docking operations, cargo handoff, refueling support, orbital science. Surface mission staging, return routes. Those are not the features of a one-time expedition. Those are the features of sustained operations. That is one of the biggest changes Artemis is trying to create. Apollo proved humans could reach the moon. Gateway is part of proving humans can keep operating there. That is a much harder standard. Reaching the moon once is a historic achievement. Building an orbital system that keeps supporting missions again and again is a long-duration engineering challenge. It forces NASA to solve traffic, timing, propulsion, habitation, logistics, and international coordination all at the same time. And once that system starts working, the surface base becomes something more serious than a target. It becomes a systems problem that does not go away after one successful mission. Now you have orbital infrastructure that must keep functioning, surface infrastructure that must keep growing, and transfer systems that must keep connecting the two. Every part starts depending on the others. That is exactly what makes the architecture more powerful, and also what makes it more demanding. So Gateway is not the moon base, but without something like Gateway, the moon base is harder to repeat, harder to expand, and harder to support. It is the scaffold above the surface campaign. It is the place where operations in lunar space stop being improvised and start becoming organized. And the moment lunar operations become organized, the real pressure shifts downward to the next challenge. Because having an orbital node is one thing. Actually, landing heavy cargo near a growing outpost without damaging the site, without missing the zone, and without turning lunar dust into a long-term disaster is where the plan can still fail. This is the part where the whole plan can fail even if everything else works. You can launch from Earth, dock in lunar orbit, send crews to Gateway, and still lose the moon base if you cannot land cargo safely and precisely on the surface again and again. Because building a base is not the same as landing once. You're not just trying to touch down anywhere on the moon, you're trying to place heavy vehicles close enough to the growing outpost to be useful, but far enough away that the landing itself does not damage the outpost. That is a much harder problem. NASA's own landing region work shows how serious this already is. Teams are balancing terrain, lighting, safety, and access in every candidate area near the South Pole, and that is before the base even starts getting crowded. Once you move from one crew mission to repeated cargo deliveries, the standard becomes much stricter. Close enough is not good enough anymore. A cargo lander that comes down too far away makes unloading harder, power connections harder, and logistics slower. But a lander that comes down too close can blast dust and debris straight into habitats, power system, comms hardware, or parked vehicles. So the base needs landing geometry that can scale. Not just one good landing, a layout that can survive many landings. That is where the public image of the moon starts to break down. People still picture something like Apollo, a compact lander, a small crew, a short stay, and then departure. Artemis is not working with that scale. NASA says Starship HLS is about 50 meters tall or 165 feet. That is roughly the height of a 15-story building. It will use an elevator to move crew and cargo between the cabin and the surface. That one fact changes the entire landing problem. This is no longer a small vehicle dropping onto open ground. This is a very tall system trying to deliver serious mass in low gravity, in vacuum, in difficult terrain, and in an environment full of abrasive dust. A tall lander brings advantages, obviously. It can carry much more. It can support bigger missions, it can move heavier cargo. But the scale creates new problems at the same time. Plume interaction becomes a bigger issue. Stability becomes a bigger issue. Cargo unloading becomes a bigger issue. Even the simple act of moving people and hardware from a high cabin down to the surface becomes a more demanding operation. The landing system stops feeling like a small exploration vehicle and starts feeling more like industrial equipment. And that is what Artemis really is. Once you get serious about building a base, the moon stops looking like a place for symbolic arrivals and starts looking like a place where construction logistics have to work under extreme conditions. Then you get to the problem that keeps showing up everywhere in lunar engineering: dust. Lunar dust is not a minor nuisance. It is one of the reasons a base can slowly fail even without a dramatic accident. NASA's technical and biomedical material is very clear about this. Apollo crews reported sneezing and congestion after regolith got inside. Researchers have kept warning about the same basic risks ever since. The particles are abrasive, they can be chemically reactive, they can threaten eyes, lungs, seals, fabrics, joints, bearings, and exposed mechanisms. So when a large lander fires its engines near the surface, it is not just creating a cloud. It can turn the ground into a high-speed blast of sharp particles. That matters because repeated landings can slowly damage the very base they are supposed to support. Dust can hit solar panels, radiators, connectors, mobility systems, suit hardware, and exposed structures. It can work into seals, it can coat surfaces, it can increase wear everywhere. And once you're dealing with a growing surface layout instead of one isolated mission, this becomes a systems problem. The landing zone is no longer just the place where vehicles arrive, it becomes part of the base's long-term survival plan. That is why future lunar infrastructure will likely need separation distances, hardened hardware, site preparation, protective shields, and eventually engineered pads or berms. Without that, every successful landing may make the site worse. That is a very uncomfortable truth. A moon base can be damaged by its own success if more traffic means more dust, more erosion, more contamination, and more wear. So landing operations are not only about navigation accuracy, they're also about whether the site gets more stable with each mission or more fragile with each mission. And this is exactly why cargo diversity matters so much. NASA's Moon to Mars planning makes it clear that lunar surface exploration needs many different kinds of delivered systems. Instruments are one category, mobility systems are another, habitats are another, power units, communication hardware, spares, science, packages, utility systems, and construction equipment all have different delivery needs. A small science package does not need the same kind of vehicle as a habitat section. A medium logistics shipment does not belong on the same delivery profile as very heavy infrastructure. That is why NASA keeps talking about increasing CLPS cargo capability and closing gaps in lunar surface cargo delivery. A serious base does not want one perfect lander trying to do every job. It wants a fleet. Smaller robotic deliveries for some tasks, medium cargo systems for regular support, heavy landers for major emplacement, maybe different vehicles for crews and cargo. That kind of diversity makes the architecture more resilient. because if only one type of lander can deliver anything important, then one technical problem can freeze the whole build-up. The base becomes too dependent on a single transport path, and that is not a theoretical concern. On the Moon, every delay matters more because the environment is less forgiving. If a critical part does not arrive, systems can sit idle. If a replacement vehicle is unavailable, expansion can stall. If a cargo mission damages the site, the next missions become harder. So the landing system has to be both precise and flexible. It has to support growth without becoming the bottleneck that stops growth. This is the point where you can define the real threshold between exploration and construction. The first true sign that the moon base is real will not be astronauts stepping down onto the surface. It will be when cargo can start arriving into a growing site without damaging the site, without missing the usable zone, and without creating new hazards faster than NASA can solve them. That is the real test. Can a heavy lander touch down, unload what it brought, leave, and make the outpost more capable instead of more vulnerable? If the answer is yes, then the architecture has crossed into something much bigger than a lunar mission. It has crossed into construction. If the answer is no, then it does not matter how impressive the rockets look or how advanced the orbiting systems are. The surface campaign will stay fragile. And that is why the landing problem is one of the hardest problems in the whole Artemis plan. It is where the dream stops being exciting language and turns into a brutal question of physics, engineering, and repetition. And once you accept that, the next step becomes obvious. If landing crews and cargo over and over is this difficult, then NASA cannot afford to use astronauts for every basic task on the surface. The first real version of the base has to be built, organised and maintained by machines before humans can treat it like a working outpost. So who actually builds the first version of a moon base if astronauts are only there for short periods? Not astronauts. Robots. NASA's own planning makes that clear. In the moon base guide, one of the early capability gaps is autonomous systems and robotics. And when you read what NASA says those systems need to do, the plan becomes obvious. Robots need to manipulate payloads. They need to operate surface assets when no crew is there. They need to unload cargo in the hundreds of kilograms range, move it across the surface, and even connect and disconnect cables remotely. That is not a side feature. That is the first draft of the base. Before the moon becomes a place where people live for long periods, it becomes a place where machines work by themselves. The first machines on site are not there to do dramatic science. They are there to do the jobs that make science and survival possible later. Move cargo, check hardware, survey terrain, keep track of assets, maintain basic order. That is how the outpost starts becoming real. Not when people arrive, but when equipment keeps functioning and the site keeps improving even when people are gone. That also tells you something uncomfortable about lunar crews. Astronaut time on the moon is far too expensive to waste on basic labour. Every minute a human spends on the surface is paid for with launch mass, food, oxygen, radiation exposure, suit wear, and return risk. NASA's own architecture language says robotics should reduce the burden on crew by unloading and moving cargo, performing remote surveys, and identifying useful resources or locations. That is not about convenience. It is about making the whole system possible. Because if a crew spends half its time dragging equipment, plugging in cables, and doing repetitive transport work, the base does not scale. The surface campaign becomes too inefficient. The crew should be doing the jobs humans are actually best at: judgment, repair, geology, problem solving, inspection, adaptation when something unexpected happens. If humans are stuck doing the work of forklifts and loaders, then every sortie burns huge cost for very little long-term progress. So the moon base only starts making sense when the routine labour begins moving away from humans and toward machines. Then you hit another problem immediately. Why not just control all the robots directly from Earth? Because the delay gets in the way. In pure physics terms, the moon is about 1.2 light seconds away one way. That already makes direct real-time control clumsy, but actual lunar mission operations can experience one-way delays more like 3 to 14 seconds, depending on the system setup and situation. That may not sound huge at first, but it is enough to make tight control awkward for anything that needs fast reaction. A robot driving over rough terrain, handling a suspended load, approaching hardware, or responding to a hazard cannot wait several seconds for every tiny decision. So the robots cannot just be puppets. They need a mixed style of control, enough autonomy on board to stay safe, avoid obvious hazards, and continue routine work. Enough supervision from Earth or from astronauts to stay on task and stay useful. That is a very important shift because it means the moon base is not just training NASA to operate on the moon. It is training NASA to build systems that can act more independently far from Earth. The moon starts behaving like a proving ground for Mars long before anyone sets foot on Mars. And this is where the public picture of robots on the moon is usually too clean. People think about rovers taking pictures or maybe collecting samples. But the first robotic jobs that matter most are not glamorous at all. They are ugly construction jobs. Site prep, regolith movement, surface grading, building up berms, clearing areas, preparing landing zones. NASA's broader lunar construction work and impact work is already aimed at things like roads, pads, berms, blast shields, shelters, and infrastructure made partly from regolith. The Moonbase Guide also includes regolith manipulation and site preparation in later phases. That is a huge clue about where this is going. NASA is already thinking beyond the idea of landing a finished habitat and simply using it as is. The goal is to change the site itself so operations become safer and more repeatable. That means the lunar surface stops being just a location. It becomes construction material and protective material. The moment robots start moving lunar dirt to protect hardware, reduce plume damage, or prepare a more stable work area, the mission changes character. It stops being a visit. It becomes engineering. And that makes the robotic role much bigger than most people assume. A robot that can move cargo is useful. A robot that can survey terrain is useful. But a robot that can reshape the site so later landings are safer, later cargo handling is easier, and later crews have better protection is doing something much more important. It is improving the base between missions. That is what real infrastructure does. It gets maintained and upgraded even when nobody is there to celebrate it. There is also a practical reason this has to happen. The moon base will spend long periods without humans on site, especially in its earlier years. During those uncrewed periods, something still has to keep the place from drifting into failure. Power systems still need monitoring. Cargo may need repositioning. Comm systems need to stay healthy. Surface assets need to stay accounted for. Faults need to be detected before they grow. If every small issue has to wait until the next astronaut team arrives, the outpost becomes slow, fragile, and hard to grow. But if robots can keep it organized and stable between crew visits, the whole system becomes more durable. That leads to one of the biggest threshold moments in the entire Artemis story. The first true moon base milestone may not be a dramatic crewed landing at all. It may be something much quieter. An uncrewed month where nothing major goes wrong. The power stays on, the communications links hold, cargo gets moved into the right places, basic systems stay healthy, the site remains usable, and Earth does not have to micromanage every second of it. That sounds less impressive on camera, but in engineering terms, it is a much bigger leap. Because once a machine-maintained outpost can survive alone through cold, dust, and long periods without humans, the program has crossed a major line. It has shown that off-world infrastructure does not have to shut down when people leave, and that changes the whole meaning of the base. Now, the moon is not just a place humans can visit when conditions are right. It becomes a place where human-built systems can keep functioning on their own. That is the real escalation here. The robots are not just assistants, they are the first workforce of the moon base. They carry the site through the period when human presence is too rare, too short, and too expensive to do everything directly. They turn short visits into cumulative progress. They turn landed cargo into organized infrastructure. They turn empty stretches between missions from dead time into construction time. And once that starts working, the next problem becomes even more unforgiving. A robot can move cargo, a robot can prep a site, a robot can keep systems alive between missions. But none of that matters if the base cannot keep its power on through darkness, cold and long polar shadow. On the Moon, power is not just another subsystem. It is the line between an operating outpost and a dead one. So what actually keeps a moon base alive when the sun is low, the shadows are long, and the temperature starts dropping fast? Power. Not in an abstract way, in the most direct way possible. If the power system fails, heating fails, communications fail, storage fails, charging fails, life support starts failing, and the whole outpost begins moving towards shutdown. That is why power is not just one subsystem among many. On the Moon, power is the thing that decides whether the base is active infrastructure or dead hardware. And the South Pole does not make this easy just because it has some areas with better illumination. That is a mistake a lot of people make. They hear that NASA wants the pole partly because of lighting conditions, and they assume that means easy solar power. It does not. The light there comes in at a very low angle. NASA's moon-based planning says that directly. The low sun angle makes solar generation harder and exposes systems to long periods of extreme cold and darkness. So even in the region NASA chose partly for lighting advantages, power is still a hard problem. That is because the light is shallow, inconsistent, and very dependent on local terrain. A ridge can block it. A crater edge can cut it off. A spot that looks good on a broad map can turn into a bad power location once you care about exact angles and exact shadow timing. Solar panels may get light for long stretches in some places, but it is not strong overhead sunlight like people picture on Earth. It is low, slanting light that can disappear behind terrain very easily. That means the real job is not just placing solar panels on the Moon. The real job is designing an energy system that can survive low-angle light, shadowing, long cold periods, temperature swings, dust, and the fact that your loads are spread across a growing site. That is why NASA is already talking in hard thresholds instead of vague promises. One of the early targets in the Moonbase Guide is demonstrating around 5 kilowatts of power generation and storage and surviving more than 120 hours of darkness. More than 5 days. That number matters because it turns the whole power discussion from a concept into a test. 5 kilowatts is not enough for a large permanent settlement, but it is enough to expose the real problems. Can you generate it reliably? Can you store enough of it? Can you keep batteries or other storage systems within temperature limits? Can you deliver that power where it is needed? Can you survive the dark period without freezing hardware or draining the system dry? That is the first real power rule of the moon base. If you cannot survive 5 days without sunlight, then you do not control the site. The site controls you. And this is where the power problem becomes much more serious than just generation. Once the sun is no longer helpful, storage takes over. Once storage takes over, mass becomes a problem. Thermal control becomes a problem. Degradation becomes a problem. Distribution losses become a problem. Suddenly the moon base is not just about producing electricity. It is about protecting your ability to keep using it when conditions get worse. And that is exactly why solar alone is not enough for the long term. NASA's own power gap work includes the need to survive the lunar night using radioisotope thermal systems. That is already one level of escalation. But NASA is also working with the Department of Energy and Industry on a 40 kilowatt class fission surface power system for the Moon for the early 2030s. NASA has also pointed out that 4 10 kilowatt units could support robust operations. That is where the power story changes from survival mode to permanent capability. Because now the question is no longer just how do you stretch sunlight. Now the question becomes how do you stop caring so much whether the sun is currently helping you or not. That is what nuclear surface power changes. First you have solar plus storage, then you add thermal survival support. Then you move toward fission because continuous presence cannot depend on long periods of energy starvation. A base that has to panic every time it loses sunlight is not a mature base. A base that can keep operating through darkness, cold, and bad local geometry is much closer to something permanent. And this matters for another reason. The energy demand does not stay fixed. Early on, maybe you are trying to power a few core systems, charge a rover, keep communications alive, and maintain thermal control. But as the site grows, the load grows too. More habitats, more surface vehicles, more science payloads, more communications gear, more processing hardware. Eventually, maybe local resource extraction systems. So the power system has to grow from something that keeps a few assets alive into something more like a microgrid. That word matters. A lunar base is not one machine with one power cord. It is a distributed system. NASA's moon base planning breaks this down clearly into generation, storage, conditioning, and distribution. Those are different jobs, and each one can fail in different ways. Generation gets you the electricity. Storage keeps it available when conditions get worse. Conditioning makes sure the electricity is usable by different systems. Distribution gets it to where it is needed. And once you start laying that distribution between habitats, vehicles, science packages, and processing equipment, the base changes character. Separate machines stop being isolated assets and start becoming one connected ecosystem. A rover can recharge from the site. A habitat can draw from a shared source. Surface instruments can stay active longer. Processing equipment can run without being self-contained. That is a very important shift, because it means every new cable and power interface increases not just capability, but interdependence. The power network becomes one of the first real utility systems on another world. And that is why the distribution side matters just as much as the generation side. It is not enough to produce power in one good location if the rest of the site cannot use it efficiently. If power has to cross difficult terrain, through dust, through extreme temperatures, through connectors that may degrade over time, then reliability becomes a huge issue. A weak connection can disable a useful asset. A damaged line can isolate part of the site. A badly planned layout can make future expansion much harder. So once again, the moonbase becomes real through ordinary infrastructure work. Cables, connectors, routing, protection, redundancy. Those details decide whether the system can grow. And all of this leads to the coldest truth in the entire section. On Earth, a power outage is usually an inconvenience. On the Moon, it is a countdown. There is no atmosphere to soften the temperature drop. There is no local grid to borrow from. There is no truck coming with a replacement generator. If critical systems lose power, you do not just lose comfort, you start losing margin. Then you start losing hardware. Then you start losing the base. So if NASA solves power at the South Pole, it is doing much more than keeping lights on in a remote outpost. It's proving that humans can keep engineered islands of life support alive in environments that are constantly trying to shut them down. That is one of the biggest capabilities any space program could develop, because if you cannot do that on the Moon, then talking seriously about Mars is still premature. And once the power system starts becoming reliable, the next thing the base needs becomes just as fundamental. It needs its own communications, timing, and navigation network. Because even a powered base is still blind and fragile if its crews, rovers, sensors, and assets cannot talk to each other, cannot locate each other, and cannot operate as one connected system. A base with power but no network is still half blind. That is the next thing Artemis has to solve. Communications, positioning, navigation, and timing are not nice extras that sit on the edge of the mission. They are core utilities. NASA's own moon-based planning makes that clear. The list of capability gaps includes surface-to-Earth communications, surface-to-surface communications, wayfinding for both crewed and uncrewed missions, and location tracking for samples and resources. That is a very important detail, because it shows NASA is not thinking about the moon base as just a pile of hardware. It is thinking about it as an information system, and that is exactly the right way to think about it. If a rover is moving beyond sight of the habitat, you need to know where it is. If a sensor is collecting useful science data, you need to time sync it correctly. If a crew collects a sample in difficult terrain, that sample location has to be documented accurately. If a habitat, a power unit, a lander and a vehicle cannot all communicate clearly with each other and with Earth, then the whole site becomes harder to operate, harder to expand, and harder to trust. In a place as dangerous as the Moon, confusion is not a minor inconvenience. Confusion becomes risk very quickly. That is why the network side of the base is much bigger than the Apollo-era picture most people still have in their heads. Apollo could work with voice communications, basic telemetry, and a simpler style of surface activity because those missions were short, tightly focused, and limited in range. Artemis is trying to support a much more complex surface campaign. More hardware, more mobility, more robotic operations, more science return, more cargo, more infrastructure, and eventually longer stays. That changes the data requirement completely. NASA's Moonbase Guide points to a second orbital relay constellation with surface imaging capability and lunar ground stations that could support more than 500 megabits per second. That number tells you this is not about keeping a crackly voice loop alive, that is serious bandwidth. At that level, you're talking about modern operations. Detailed engineering data can move fast. High-rate science data can move fast. Software patches and updates can move fast. Terrain maps can be transmitted and refreshed. Medical support can become much more capable. Supervised robotic systems become more practical. The Moon is no longer being treated like a distant place you call occasionally. It is being treated like a working site that needs real data flow. And that changes how you understand the whole outpost. A 500 megabit per second target means NASA is not planning to whisper to the Moon. It is planning to run a real information economy there. That is the level of network you build when you expect regular operations, not rare appearances. A habitat with modern sensors, rovers, cameras, navigation tools, power management systems, and robotic interfaces is going to produce a lot of data. If that data moves too slowly or too unreliably, the whole system becomes less efficient and less safe. Then there is the navigation problem, which is even worse than most people realize. At the lunar South Pole, the environment does not give you simple visual cues. The sun stays low. Shadows can stretch across ridges and crater walls. Permanently shadowed areas remove obvious landmarks. Line of sight can disappear quickly in broken terrain. That means a crew or robot cannot just rely on instinct and direct visibility the way people often assume. The surface geometry can fool you. A route that looks clear can hide slope danger, communication loss, or a bad return path. So navigation on the Moon is not just about convenience, it is a survival system. That is exactly why NASA has worked underway on lunar communications and navigation infrastructure through efforts like LCRNS. The details will differ from Earth's GPS, but the idea is similar in spirit. The Moon needs its own navigation layer. Once rovers and crews move beyond direct sight of the habitat, location awareness becomes critical. You need to know where people are, where vehicles are, where assets are, where hazards are, and how all of those positions change over time. A wrong turn on Earth might waste time. A wrong turn on the Moon can cost power margin, thermal margin, communication access, and return safety all at once. So once again, the quiet technical system turns out to be one of the most important systems in the entire base. If crews and robots have good positioning, good timing, and reliable data links, they can work farther, faster, and more safely. If they do not, the whole surface campaign shrinks. Distances that are physically reachable become operationally too risky. Science targets become harder to trust. Resource mapping becomes weaker. Rescue or recovery becomes more difficult. A lunar base without a strong navigation and timing layer is going to stay smaller and more fragile than NASA wants. Then you hit the command problem. Even with good communications, Earth is still not next door. In raw physics terms, the one-way light time to the Moon is about 1.2 seconds, but actual operations can push the effective one-way delay to several seconds depending on the mission setup. That sounds small until something important is happening right now. A rover is descending a slope, a robot arm is handling cargo, a lander is making a hazard decision, A crew is trying to respond to a system fault. In those moments, even a few seconds can make direct step-by-step control awkward or impossible. That means the command culture has to change. Earth can still advise, Earth can still analyze, Earth can still supervise, but Earth cannot always be the hand on the controls for every important moment. That is where the moon base stops being a remote-controlled science camp and starts becoming a real field outpost. The systems on site need more local decision-making, the crews need more authority, the robots need more autonomy. The network has to support that style of operation instead of pretending the moon is just a slightly farther version of low Earth orbit. And that has a deeper meaning than it seems. Once you build persistent relays, high-rate data links, timing services, and reliable location awareness into the lunar environment, the moon stops being just a place humans visit. It becomes a place humans organize. That is a very different stage. Visiting a place means you show up, do a task, and leave. Organizing a place means you map it, track it, connect it, assign routes across it, maintain awareness across it, and make different assets work together inside it. That is one of the quietest thresholds in the entire Artemis story, but it may be one of the biggest. A communications and navigation grid turns scattered machines into a working territory. It lets robots and crews move with confidence. It lets science become systematic. It lets logistics become coordinated. It lets power systems, mobility systems, habitats, and cargo operations stop acting like separate islands. The information network is what makes the physical network usable. And once that happens, the moon base starts looking less like a series of landings, and more like the early skeleton of a real settlement. Not because it is large yet, not because it is comfortable yet, but because it can finally see, talk, time, track, and coordinate itself. That is how remote machinery becomes infrastructure. That is how a dangerous site starts becoming manageable. But even a powered, connected, location-aware outpost still has one huge problem left. It can move data, move cargo, and move machines, but people still need a place to stay alive in deep space for longer periods. And the moment you stop thinking in terms of short visits and start thinking in terms of actual stays, the moon base changes again. At what point does a moon mission stop being a visit and start becoming a stay? It happens when the crew no longer lives only inside a lander. That is the shift NASA is now planning for very openly. In the Moon to Mars architecture updates, NASA includes an initial surface habitat element meant to house astronauts and increase crew size, range, and mission duration. The Moonbase Guide also treats habitation as its own major capability area. With short duration and moderate duration pressurized environments, and with systems that can keep operating between missions. That is a major change in the story. A lander cabin is temporary by design. A surface habitat is something else. It is a living volume that stays on the moon, stays useful when empty, and becomes productive when crews arrive. That sounds simple, but it changes almost everything. A habitat is not just a bigger room, it changes how long a crew can stay, how much work they can do, how far they can travel, and how much redundancy they have, and how much of the mission depends on surface infrastructure instead of the arrival vehicle. Once the crew starts relying on a habitat, the base becomes less like a short expedition and more like a place with a permanent address. That is why this matters so much. It is the moment the architecture stops being centered on transport and starts being centered on habitation. And the real challenge is not the dramatic part, it is the biological part. A habitat means NASA has to solve the ordinary human problems that become very serious in a lethal environment. Hygiene, exercise, nutrition, medical capability, waste management, contamination control, Earth-independent operations. NASA lists exactly those kinds of needs in its habitation targets, and those details matter because they make the moon base real. A crew staying longer is not just a crew breathing longer. It's a crew eating, cleaning, exercising, sleeping, treating minor injuries, managing supplies, and keeping the inside environment healthy day after day. That is where the mission stops being mainly about getting there and starts being about metabolism. Food has to be stored and managed. Waste has to be contained and processed. air quality has to stay stable, water systems have to stay reliable, dust cannot be allowed to take over the living space. Crew health has to be protected over time, not just for a few hours outside on EVA. Even exercise changes role. In 1/6 gravity, astronauts will still need to protect muscle and bone, but the exact long-term effects are still not fully known, because no human civilization has ever lived in this gravity level for extended periods. That leads straight to the next big question. Does lunar gravity actually solve the human problem, or only part of it? The Moon's gravity is about 1.62 meters per second squared, around 0.17 g. That is enough to change how people walk, how equipment loads behave, how blood shifts through the body, how dust settles, and how exercise systems have to work. But it is nowhere near Earth gravity, so nobody really knows what normal life looks like over long periods at 1/6 g. NASA's own moon-based planning says continuous presence will provide data on astronaut performance, long missions, gravity adaptation, and EVAs in partial gravity. In other words, the habitat is not just a shelter, it is also a laboratory for the basic human question Artemis is trying to answer. Can people stay healthy in that environment for long enough to build something durable? Can they work efficiently? Can they sleep well? Can they recover from fatigue well? Can they adapt without slowly losing too much physical performance? These are not side questions. If the answer is bad, then every bigger plan becomes harder. If the answer is better than expected, then the Moon becomes much more useful as a long-term outpost. So the habitat is doing two jobs at once. It keeps the crew alive, and it tells NASA what kind of human operations are actually possible in 1/6 g. Then there is a design rule that matters even more than people realise. The habitat has to survive when nobody is home. NASA's planning includes uncrewed operation between crewed missions as a specific habitation function. That sounds procedural, but it is one of the biggest changes in the whole architecture. A crew cabin that you leave behind and do not expect to keep itself healthy is just part of a vehicle. A habitat that stays thermally stable, watches for leaks, manages power, protects its internal environment, and handles faults after the crew leaves is infrastructure. That means the habitat has to behave more like a facility than a spacecraft. Thermal control cannot just shut off. Sensors have to keep watching. Internal systems have to stay within limits. Faults have to be detected and managed before they become fatal to the next mission. The habitat may sit empty through dust, cold, and long stretches of lunar time, and then be expected to support astronauts again when they return. That is a completely different design philosophy from a short mission stack. It means the moon base is no longer just trying to land useful hardware. It is trying to keep surface buildings alive across mission gaps. And once you start thinking that way, the habitat stops being one sealed box, starts becoming part of a utility network. NASA's logistics gap list includes mating between pressurized assets and the transfer of pressurized cargo, water and gases to habitable surface systems. That sounds technical, but it is actually one of the biggest signs that the moon base is moving towards settlement logic. A sealed vehicle that keeps everything inside itself is one thing. A habitat that can receive water, gases, and cargo from other surface assets is something much more advanced. Because now the habitat is not just where people sleep, it is a node in a network. A crew vehicle can connect to it, supplies can move into it, water can move into it, gases can move into it, pressurized cargo can move into it without being handled the hard way outside every single time. That makes operations safer, faster, and more sustainable. It also changes the character of the whole outpost. Once your living spaces and your visiting vehicles can exchange consumables and cargo through planned connections, the site starts behaving less like a temporary mission stack and more like a small settlement with actual utilities. And that is a bigger shift than it sounds. Plumbing is not glamorous. Gas transfer is not glamorous. Pressurized interfaces are not glamorous. But when those systems appear, the moon base starts acting like a place that expects people to return, connect, refill, unload, and keep going. Separate vehicles and structures begin functioning as one living system instead of isolated modules. That is exactly how a frontier outpost becomes more permanent, not through one big announcement, but through ordinary systems that make longer stays less risky and less wasteful. So the real meaning of the habitat is not just extra comfort, it is duration, continuity, and interdependence. It is the point where the crew starts living in surface infrastructure instead of merely arriving in a spacecraft. It is the point where biology becomes a daily engineering issue. It is the point where the moon starts teaching NASA what long stays in partial gravity actually do to human beings. And it is the point where utilities begin connecting living space to the rest of the site. Once that happens, the base becomes much more capable, but also much more demanding. Because now it has living systems that must be resupplied, protected, monitored, and supported over time. And the moment you give crews a place to stay longer, the next limit shows up immediately. The moon is too big, the polar terrain is too broken, and the useful targets are too spread out for a base to survive if everything important is only walking distance away. A habitat can keep you alive, but it cannot solve the biggest problem at the lunar South Pole: distance. That is the hidden enemy. A base can fail even if the habitat works, the power works, and the comms work if every useful target sits just beyond what a crew can safely reach on foot. At the pole, that problem gets worse because the terrain is broken, the light is difficult, and the things NASA cares about most, like good science sites, useful ridges, shadowed craters, and possible ice-bearing areas, are not all packed into one easy walking zone. That is why NASA treats mobility as a primary system, not a side tool. In the Moonbase Guide, NASA talks about small utility rovers and hoppers, along with larger crewed and uncrewed rovers moving at around 10 km per hour, about 6 miles per hour. That speed does not sound impressive on Earth. It is slower than a city bike. But on the Moon, in 1/6 G, across polar terrain, with limited EVA time and constant safety constraints, that kind of mobility is freedom. It means the base stops being one small safe circle around the habitat. It starts becoming a working region, and once the workable region expands, everything expands with it. Science options multiply, resource access multiplies, power siting options multiply, landing zone choices multiply. Suddenly the base is no longer trapped by the first spot where astronauts can stand safely. It can start interacting with the broader landscape. That is why rovers can expand the base faster than habitats do. A bigger habitat lets you stay longer. Better mobility lets you reach more places, support more hardware, and unlock more value from the terrain. That is the difference between surviving in one spot and actually developing a site. The first big step in that process is the Lunar Terrain Vehicle, or LTV. NASA describes it as something between the Apollo rover and a more autonomous Mars-style rover. That hybrid idea matters a lot. Apollo's rover was useful, but it only really existed when astronauts were there to drive it. A Mars-style robotic rover can keep working without a human crew on site, but it is slower and built around different mission logic. The LTV sits between those two worlds. It is meant to support astronauts when crews are present, but it can also continue operating robotically when crews are gone. That is exactly the kind of vehicle a young moon base needs. It means you do not have to choose between human mobility and robotic mobility. The same platform can scout routes, move equipment, check terrain, support science tasks, and keep adding value between crewed missions. That is very important in the early years, because the surface campaign will still spend long stretches with no humans on site. A vehicle that goes dead every time the crew leaves is much less useful than one that keeps extending the base's reach. And that changes how you think about time on the moon. If every kilometre travelled has to happen during human sortie, expansion is slow and expensive. But if a rover can keep driving, scouting, mapping, rehearsing and hauling gear outside those short crew windows, then progress becomes cumulative. Routes can be tested before astronauts use them. Equipment can be moved before astronauts arrive. Hazard areas can be checked in advance. A lot of the risk moves earlier in the timeline, where robots can absorb it more safely than humans can. Then you get to the real game changer, the pressurized rover. This is where mobility stops being just transport and starts becoming an extension of the habitat itself. NASA says a pressurized rover will greatly expand the ability to explore, conduct science, and live and work on the lunar surface. JAXA describes the NASA JAXA pressurized rover as a vehicle astronauts can inhabit without wearing spacesuits inside, and current expectations include about 28 crewed days per year, with the rest of the time available for uncrewed operations. That is a huge shift. A pressurized rover is not just a ride. It is a mobile life support system. It is a field lab. It is a way to detach exploration range from the fixed base. Instead of every serious activity happening close to the habitat, crews can move outward while still carrying a controlled environment with them. That makes much longer traverses more realistic. It gives crews a safer way to work farther from home. It also changes the meaning of distance. A ridge 10 or 15 kilometers away is a very different problem if you have to walk it in suits than if you can travel there in a pressurized vehicle that supports rest, planning, instruments, and return margin. That is why the pressurized rover is so important. It turns the base from a single point into a moving pocket of life support. Crews can leave the immediate zone around the habitat, cross difficult terrain, work longer, and come back with much more value. Science improves because more places become reachable. Resource prospecting improves because suspected ice-rich areas become easier to inspect. Infrastructure planning improves because engineers can examine more candidate routes and work sites directly. The pressurized rover does not replace the habitat, but it makes the habitat matter more by extending its useful reach outward. And this is also where the moon starts looking less like a mission site and more like an operating environment. On a normal mission, you arrive at one location and do your best within the limits of that spot. In a developing base, mobility lets you start comparing locations, linking locations, and exploiting the differences between them. One area may be better for light, another for science, another for ice access, another for communications or landing safety. Rovers are what let one outpost use all of those places instead of being trapped by only one of them. Then there is the smaller side of the mobility story, which matters just as much in the long run. Not every job needs a large crewed rover. NASA's mobility planning also includes small utility rovers and hoppers for science, reconnaissance, and resource discovery. That tells you something important about how the base will actually mature. It will not rely on one heroic vehicle doing everything. It will grow a local vehicle ecology, one rover for crew movement, another for cargo, another for scouting, another for surveying, maybe later one for excavation, one for site prep, one for construction support. That is how real industrial environments work. You do not scale by building one perfect machine and asking it to carry the entire system. You scale by using many specialized machines that can do their own jobs well, and that can fail without ending the whole operation. That is exactly what a moon base will need too. A small scout rover can take risks a crewed vehicle should not. A utility rover can move supplies without wasting astronaut time. A hopper may reach awkward terrain faster than a wheeled vehicle in some cases. Once those systems start working together, the mobility network gets stronger, more flexible, and less fragile. And that matters because the South Pole is not kind to single points of failure. If one flagship rover breaks and everything depends on it, then exploration range collapses, logistics slow down, and the base loses a huge part of its usefulness. But if the site has multiple mobility layers, then one loss hurts without stopping everything. That is another sign that Artemis is moving away from mission logic and toward infrastructure logic. So the real punch here is simple. Habitats let you stay alive. Rovers let you become operationally dangerous. The second Artemis crews can leave the immediate landing zone, cross ridges, inspect shadowed regions, service distant instruments, move hardware between sites and bring back resources from kilometers away. The moon base stops acting like a camp, starts acting like a territory under development. That is when the map changes. Not because the moon itself changed, but because the part of it humans can actually use gets much larger. And once mobility expands the usable region, the next question becomes even more serious. A bigger reach only matters if there is something out there worth reaching. At the South Pole, the answer NASA cares about most is water ice. Because if the base can get water from the Moon instead of hauling every kilogram from Earth, then the whole economics of survival start to change. The value of the South Pole comes down to one thing: water. Not because water sounds nice to have, but because without it, a moon base stays much more dependent on Earth. NASA's orbital data keep pointing to the same possibility. The coldest permanently shadowed regions near the poles may hold water ice, especially in places below about 75 Kelvin, around minus 198 degrees Celsius, or minus 325 degrees Fahrenheit, and near the bases of slopes that face away from the sun. Some of those shadowed crater areas are even colder than minus 246 degrees Celsius, colder than minus 410 degrees Fahrenheit. That is why the South Pole matters so much. The hardest places to reach may be the places that make the base worth building. And the reason is simple. Water is not just for drinking. Water is mass you can use for multiple jobs. It can support crews directly. It can help with shielding. It can be split into oxygen for breathing and oxygen and hydrogen for propellant. The same material that keeps astronauts alive can also support vehicles and surface operations. So when NASA looks at possible ice near the South Pole, it is not looking at a nice extra. It is looking at one of the few local resources that could change the economics of the whole base. But orbital data are not enough. This is one of the most important points in the whole Artemis plan. A map from orbit can tell you where conditions look promising. It cannot tell you exactly how usable the resource really is. NASA needs ground truth. It needs direct measurements on the surface. It needs to know how much ice is there, how deep it is, how mixed it is with the soil, how hard it is to extract, and whether the concentration is good enough to matter. That is why polar prospecting missions are so important. VIPER matters for exactly this reason. Even with all the turbulence around the program in 2024 and 2025, it was reassigned in 2025 for delivery by Blue Origin to the South Pole under CLPS, and NASA still listed it in 2026 as a near-term lunar payload. Then there is LoopX, the joint JAXA-NASA polar exploration mission, with NASA's neutron spectrometer planned for the rover. Those missions are not just doing interesting science, they are gathering the basic facts a real outpost would need before it starts treating lunar water as a working resource. Until those local measurements come in, ice on the Moon is still partly a headline. It is not yet an industrial supply. That distinction matters because the extraction problem is much harder than the headline makes it sound. A lot of people hear water ice on the Moon and picture something simple, almost like digging frozen material out of the ground. But that is not how this is likely to work. NASA's in situ resource utilization work makes it clear that the agency is developing ways to excavate or drill into regolith-based deposits and then process, transport and store what comes out. That wording already tells you this is not a simple mining problem. The ice may be mixed through the regolith. It may exist in grains. It may be trapped in very cold soil, in small concentrations rather than sitting there as a clean layer. That means you may have to dig material up, heat it, drive the water out as vapor, capture it, purify it, condense it, store it, and then move it where it is needed. So this is much closer to chemical processing in an extremely cold and difficult environment than to simply cutting blocks of ice. The cold helps preserve the resource, but it also makes the hardware problem worse. Your equipment has to survive deep cold, dust, difficult terrain and long operations, all while doing controlled thermal processing. That is why prospecting matters so much before any industrial claims are made. NASA needs to know not just whether water is present, but whether it is present in concentrations and forms that are worth the energy and machinery needed to recover it. A deposit can be scientifically interesting and still be operationally disappointing. For the moon base, that difference is huge. The base does not need a headline. It needs a usable supply chain. And if NASA does prove that usable water can be harvested, the entire mass budget starts to change. That is where the stakes jump. as long as every kilogram of water has to be launched from Earth. The outpost stays expensive in a very basic way. Water is heavy. It costs mass to launch, mass to land, and mass to store. And because it is needed in significant quantities, it becomes one of the big recurring burdens on every long-duration mission. But if some of that water can come from the moon itself, then the logic changes immediately. Now the base is no longer just consuming supplies from Earth, it is starting to support itself in at least one category. Even partial local water production matters. It can reduce launch mass, it can improve safety margins, it can lower the number of Earth shipments needed to maintain operations, and once you split water into oxygen and hydrogen, the importance increases again. Oxygen supports life support. Oxygen and hydrogen together can support propellant production. That means local water is not just a crew resource, it is a systems resource. This is exactly why NASA's ISRU planning keeps emphasizing reduced mass, reduced cost, increased safety, and fewer launches from Earth. Those are not marketing phrases, they are the difference between a base that grows slowly and painfully and a base that starts changing the terms of its own survival. The moment the moon can supply even part of what the base needs, the whole architecture gets stronger. That is also why this section changes the meaning of Artemis. At first, the moon base looks mainly like a transport problem. Can Earth launch enough mass? Can the landers deliver it? Can the crews survive? Then it becomes a habitat and infrastructure problem. Can you power the site, connect the site, and maintain it? But once water enters the picture, the whole thing becomes something bigger. Now you are asking whether an off-world outpost can begin using a local resource to sustain itself. And that is a much more serious question than most people realize. Because if the polar ice is accessible in useful concentrations, then Artemis is no longer just demonstrating that humans can live on the moon for a while. It is testing whether a real off-world economy can begin with one molecule, H2O. That would change how we think about the moon completely. The moon would stop being just a destination where missions spend resources. It would start becoming a place where resources enter the system. That is why the South Pole is not valuable because it is mysterious. It is valuable because it may contain the first local resource that can materially change the cost and scale of human presence beyond Earth. And once that possibility becomes real, the whole mission gets more demanding. Because water is only part of the resource story. The next question is even bigger. If the moon can provide water, can it also provide building material, oxygen from its soil, and physical protection for the base itself? Water is only half the local resource story. The other half is the ground itself. Lunar regolith may look like just dust and broken rock, but NASA has been treating it as potential feedstock for years. That matters because regolith is not just loose material sitting under the base. It contains oxides, and oxygen is the dominant element bound inside many of those minerals. NASA has also already demonstrated oxygen extraction from simulated lunar soil in a vacuum environment in 2023. That is a very important proof point. It means the moon is not only a place where hardware gets dropped off, it may also be a source of useful material for life support, construction, shielding, and industrial processing if the chemistry can be turned into a reliable system. That changes the whole picture very quickly. If water ice becomes one local input, regolith becomes another. Water helps with life support and propellant. Regolith may help with oxygen, protective material, structural material, and maybe some metals and ceramics over time. That means the moon is not just hosting the base. It may eventually supply parts of the base. And that is a much bigger shift than it sounds, because every kilogram that can be made or used locally is a kilogram that does not need to be launched from Earth and landed through all the risks and costs that come with lunar delivery. You can see that shift most clearly when you get to construction. This is where in situ resource use stops sounding clever and starts sounding necessary. NASA's MEM-packed construction work is not focused on fancy ideas for their own sake. It is aimed at specific, practical infrastructure. Landing pads, habitats, shelters, roadways, berms, blast shields, and other surface features that could use regolith-based materials. NASA has also been looking at 3D printing and sintering approaches that turn local lunar powder into tiles, shapes, or other useful parts. That is where the old mental model breaks apart. Because the goal is no longer only to bring a base to the moon. The goal is to reach the point where more of the base can be made out of the moon itself. Once regolith can become part of a landing pad, part of a protective berm, part of a roadway, part of a shield layer, or part of a structural surface, Earth stops being the only place where the base gets its physical form. That is a huge difference. Up to that point, every meaningful piece of structure has to survive launch, transit, landing, unloading, and deployment. After that point, the moon starts contributing to its own built environment. That does not mean the first locally made products will look impressive. In fact, they probably will not. The early wins will likely be crude, heavy, and not very elegant. But that is completely fine, because elegance is not the point. Mass savings and operational value are the point. Early regolith products might be berms that block plume ejector. They might be rough landing pads that reduce dust damage. They might be bricks, tiles, or packed surfaces that make traffic easier and protect equipment. They might be shielding layers piled over habitats or sensitive hardware. They might be oxygen production, with some industrial byproducts that become useful later. That is exactly how frontier industry usually starts. The first useful products are not beautiful, they are the ones that remove the biggest logistical pain. On the moon, one of the biggest pains is having to launch every protective material, every structural surface, and every expendable shielding mass from Earth. If local regolith can replace even some of that, the whole base gets stronger. Not all at once, not magically, but in very practical ways. Less launched pad material, less launched shielding mass, less need to deliver simple bulk material from Earth when local bulk material is already everywhere under your feet. And this is where all the separate Artemis problems start connecting back to each other. Landing gets safer if you have prepared pads. Dust becomes easier to manage if landers are not blasting raw regolith every time they arrive. Sensitive hardware becomes easier to protect if berms and shields can be built locally. Habitats get better radiation protection if local material can be placed over or around them. Oxygen extracted from regolith can reduce the amount of consumable mass that has to come from Earth. Construction using local material can reduce how much fully finished infrastructure has to be landed from Earth in the first place. That is why ISRU is not a side science project. It feeds directly back into landing, power, habitation, logistics, and survival. It is a multiplier. Every subsystem gets some benefit if local materials become usable. Landing gets cleaner, habitats get safer, logistics get lighter, the site gets more durable, growth gets more affordable. That is exactly why NASA treats ISRU as a foundational technology area and not just a bonus capability for later. Without it, the base remains more dependent, more fragile, and more expensive. With it, the base starts improving its own position over time. There is also a deeper reason this matters. Bulk material is one of the hardest things to justify launching from Earth forever. Precision electronics, complex pressure vessels, advanced machinery, and critical life support systems will still need a lot of Earth industry behind them for a long time. But crude protective mass, rough structural mass, simple barriers, surface pads, and basic road material are different. Those are exactly the kinds of things you would want to stop importing first if a local processing works. And the moon is covered in the raw material for that shift. The challenge is turning it into usable products with machines that can actually survive and operate there. That means the first real industrial logic on the moon may be very simple. Use local dirt to protect landed hardware. Use local material to stabilize traffic areas. Use local processing to recover oxygen. Use local regolith to create shields, pads, and barriers that make every later mission easier. Once those loops start closing, the base becomes less like a collection of delivered equipment and more like a growing industrial site. That does not require full self-sufficiency, it only requires enough local contribution to change the trend. And that is the philosophical shift hidden inside all of this. For most of the space age, alien worlds were treated as scenery. Missions went there, looked around, did science and left. Artemis is testing a very different idea. It is testing whether an alien world can become inventory, not fully, not immediately, but enough that its dirt, ice and minerals enter the operating chain of a human outpost. The second that starts happening, exploration changes category. It is no longer just about visiting another place. It becomes the first working draft of the industry beyond Earth. That is a bigger break than most people realise. Once the moon's surface starts entering life support, construction, protection and transportation systems, the moon stops being just a destination. It becomes part of the machinery that keeps humans there. And the moment that happens, the next threat becomes impossible to ignore. Because even if you can use local dirt and local ice, the environment is still trying to damage every seal, every suit, every joint, every filter, and every human body on the site. The moon does not only try to kill a base with big failures, it also attacks slowly. That is what makes dust and radiation so dangerous. They are easy to underestimate because neither one has to cause one dramatic accident to become a mission-level threat. They can damage the outpost piece by piece, mission by mission, until the margin is gone. Start with dust, because dust on the moon is nothing like dust on Earth. It looks harmless when you say the word. It is not harmless. NASA's biomedical and technical work keeps pointing back to the same lesson from Apollo. Astronauts got regolith inside the cabin and reported sneezing and nasal congestion. Since then, researchers have kept studying the risk to lungs, eyes, skin and hardware. The particles are jagged, they're abrasive. They can also be chemically active. On Earth, dust is usually just dirt in the wrong place. On the moon, dust becomes a wear mechanism, a contamination problem and a health risk at the same time. That changes how the whole base has to be designed. Dust can get into seals, it can scratch visors, it can foul radiators, it can work into joints, bearings, connectors and fabrics. It can ride back inside on suits and tools. So dust control cannot be treated like cleanup. It has to be treated like survival engineering. Every airlock cycle matters. Every exterior operation matters. Every landing matters. The base has to assume that dust is always trying to get in, always trying to grind something down, and always trying to spread from the outside world into the living space. And that is a much bigger problem than most people realise, because the damage is cumulative. A single dusty EVA may not end the mission, but repeated exposure can wear surfaces, degrade mechanisms, and increase contamination inside the habitat. That means dust is not just something astronauts brush off. It becomes part of maintenance, suit design, airlock design, filtration, cleaning procedures, and even surface layout. If the base does not control dust well, the moon does not need a major disaster to beat it. Normal operations will do the damage for it. Then there is the other invisible enemy, and this one is even less forgiving: radiation. On the moon, there is no thick atmosphere above you, and no planetary magnetic shield around you like the one Earth provides. NASA's lunar radiation studies are very clear about this. The lunar surface is exposed to galactic cosmic rays and solar energetic particles from all directions. Artemis 2 solar monitoring notes also made the deep space exposure point very clear. Even the baseline radiation environment for that mission was expected to be roughly comparable to about a month on the ISS, and that was without a major solar event. That is the part people need to understand. The normal background is already serious. Then on top of that, the sun can become dangerous fast. If a strong solar event happens, the rules of the mission can change immediately. A base cannot treat radiation as a distant background issue. It has to plan for it directly. That means storm shelters, shielding mass, space weather forecasting, exposure limits, operational rules that may force crews to change plans quickly. On Earth, bad weather might delay a job. On the moon, a bad solar event can change whether it is safe to be outside at all. That is why local shielding matters so much. This is one of the strongest reasons NASA keeps coming back to regolith-based construction and protection. If you can move lunar soil over habitats, build up berms around critical systems, or create partial shelters using local material, then you are turning the moon's own surface into protection against the deeper space environment around it. That is a very powerful idea because shielding is heavy, and heavy things are expensive to launch and land. Every kilogram of protective mass that does not have to come from Earth is a major gain. Every extra layer of local shielding can improve the crew's odds and increase how long the outpost can operate safely. And this is where the difference between a visit and a stay becomes very clear. A short mission can sometimes accept higher exposure and tighter limits because the crew will not remain there for long. A real base cannot depend on that logic forever. If crews are going to return repeatedly, stay longer, and eventually push towards more continuous presence, then shielding stops being a nice improvement and becomes part of the architecture. Radiation does not care how advanced the habitat is, or how historic the mission sounds. It only cares how much protective mass sits between the crew and deep space. Then you get to the suits, and this is where the outside environment starts reaching directly into the living system of the base. NASA selected Axiom to provide the lunar spacesuit system for Artemis surface operations, and testing continues for South Pole mobility and task performance. That matters for a reason that goes beyond EVA comfort. On the Moon, a suit is not just what astronauts wear outside. It is the first barrier against dust, temperature extremes, mechanical abrasion, and radiation exposure during surface work. It is part of the base's survival chain, and the most dangerous part of that chain may be the point where the suit meets the habitat. The suit habitat airlock interface is one of the most sensitive choke points in the entire outpost. If dust crosses that boundary too easily, then the contamination does not stay outside. It moves inward. Then filters have to catch it. Surfaces have to resist it. People have to breathe around it. Equipment has to live with it. That means suit design, airlock procedures, cleaning methods, and hardware interfaces all become part of the same defensive system. A good suit on the Moon is not just a mobility tool, it is part of contamination control for the entire base. This is also why surface operations can never be treated casually. Every EVA is not only a mission task, it is also an exchange with a hostile environment. Dust comes back. Wear comes back. Thermal stress comes back. Radiation exposure accumulates. The crew may complete the job outside and still bring back damage in slower forms. So the Moon base has to think beyond single missions and think in totals, total exposure, total wear, total contamination, total fatigue. That is how the real risk grows. And that leads to the hardest truth in this section. The Moon base does not only fail by explosion, collision, or one obvious catastrophe, it can fail by accumulation. One more dusty seal, one more scratched visor, one more worn bearing, one more degraded filter, one more solar event that forces a rushed change of plan, one more EVA that goes longer than expected, one more system operating a little closer to its limit. That is what makes the Moon so ruthless. The environment does not always attack in one dramatic moment. Sometimes it just keeps taking small bites until there is no margin left. That is why dust and radiation are not side hazards. They shape almost every part of the base. Landing design, habitat design, suit design, airlocks, shielding, maintenance, cleaning, construction, EVA planning, medical rules, site layout, all of it. A Moon base that cannot control dust and manage radiation is not durable, no matter how advanced the rest of the architecture looks. And once you accept that, the next question becomes even more serious. Because if the environment is this unforgiving, then the people living and working there cannot depend on Earth the way astronauts in low Earth orbit do. They will have to make more decisions locally, solve more problems locally, and trust local systems more than real-time instructions from home. So who is really in command on the Moon when something goes wrong? That question matters more than most people realize. On the ISS, mission control can stay deeply involved in almost everything because low Earth orbit is close. The delay is tiny, the support system is mature, the rescue options are better, lunar operations are different. NASA's own moon-based planning says Earth-independent operations become more important as the architecture matures, and that the base will be used to test autonomous systems, human-robot interaction, and astronaut autonomy. That is one of the biggest changes hidden inside Artemis. The crew is not just going farther from Earth, the crew is being forced to carry more decision-making power because distance, delay and risk leave no other option. That changes the culture of spaceflight. In low Earth orbit, the model is built around tight support from home. On the Moon, that model starts breaking down. Earth can still advise, Earth can still analyse, Earth can still help, but Earth cannot always direct every move in real time, and it cannot quickly fix every surface problem. That means the crew has to think more like an expedition team in a remote hostile environment than like operators inside a heavily supported orbital lab. Decisions move outward, responsibility moves outward, risk management moves outward. That is the quiet revolution in Artemis. And the same thing is true in medicine, which makes the problem even more serious. NASA's habitation targets include extended medical capability and Earth-independent operations for a reason. On the Moon, the crew cannot depend on fast evacuation or immediate hands-on support from home. The average distance is about 384,400 kilometers, around 239,000 miles. That sounds close in cosmic terms. In emergency terms, it is isolation. There is no rescue helicopter. There is no quick hospital transfer. There is no easy way to reverse a mistake once it starts getting worse. So a lunar crew needs more than basic first aid. It needs more onboard diagnosis, more local treatment capability, better procedures that can actually be executed on site, and better planning for situations where Earth can guide but cannot save the day quickly. A problem that might be manageable on the ISS with strong ground support can become much more dangerous on the Moon if the crew, the systems and the medical hardware are not built for self-reliance. That is why independence is not a philosophical idea in this architecture. It is part of the survival plan. Then there is another important shift. More autonomy does not mean the astronauts are doing everything themselves. It means the division of labour changes. NASA's own capability gap list makes this very clear. Robots are supposed to unload cargo, do reconnaissance, manipulate equipment and keep working during uncrewed periods. That is not replacing astronauts. It is changing what astronauts are for. Once the robots take over the repetitive transport work, the monitoring work, and a lot of the routine handling work, the humans are freed for the jobs that still need human judgment. And those jobs are harder than the public usually imagines. Lunar astronauts in a real base are not just explorers with flags. They become a combination of field commander, mechanic, medic, geologist, systems manager, and emergency decision maker. They have to interpret what the robots are doing, fix what the robots cannot fix, judge risk in real terrain, adapt plans when conditions change, and keep the whole surface campaign coherent when multiple systems start interacting. That is a much more demanding role than the classic picture of a moonwalker. It is also much more useful as preparation for Mars, because Mars will demand even more independence. This is why the moon base is not only a construction project, it is also a training ground for a new kind of astronaut. Not one who waits for every answer from Earth, but one who can operate with delayed support, incomplete information, local assets, and real consequences. That does not make Earth irrelevant. It makes Earth a partner instead of a controller, and that is a major step in how human spaceflight works. Then the stakes rise again once you move from short stays to longer duration operations. NASA's Moonbase Guide says continuous presence will provide unprecedented data on astronaut performance in deep space, long missions, gravity adaptation, and partial gravity EVA. That means the base is not just testing machines, it is testing people under conditions humanity has never lived through for long periods. How well do crews sleep in 1/6 G when the work is real and the danger is real? How does cognition change over time? How do bone loading, muscle maintenance, immune response, and coordination hold up? How do teams make decisions after months of operating with risk and distance in the background every day? Those are not side questions, they are part of the core mission. The Moonbase will reveal not only what humans can build on another world, but what kind of human performance another world demands. Maybe some things work better than expected. maybe some things work worse. Maybe some tasks that seem manageable for short missions start degrading over long timelines. Maybe group dynamics change in ways mission planners have to design around. Maybe maintenance performance slips when fatigue, confinement, and repeated EVA stress build up. The base becomes a human research platform whether NASA wants that label or not, and this is where the psychological stakes become much higher. A short mission still feels like a trip. A longer duration outpost starts feeling like lived reality. The moon stops being a point on a map and starts becoming part of the crew's actual world. They're not just visiting it, they're depending on it, depending on local power, depending on local robots, depending on local procedures, depending on their own judgment more than on instant instructions from Earth. That is a different level of commitment. It also changes what home means during the mission. On a short expedition, home still feels close in a practical sense because the mission is narrow and temporary. On a functioning moon base, home starts becoming psychologically farther away even if Earth is still visible in the sky. The crew is building habits, routines, and trust around systems that exist on the moon, not on Earth. They are learning to solve local problems with local tools and local teams. That is one of the most important human transitions in the whole Artemis story. Because the quiet truth is this: the species does not become multiplanetary the first time it lands somewhere. It moves in that direction when crews start making local decisions, trusting local infrastructure, and staying functional without expecting home to run everything in real time. That is the deeper meaning of a moon base. It is not only testing engines, habitats, and robots. It is testing whether humans can really operate away from Earth in the full sense of the word. And once that begins to work, the final meaning of Artemis becomes much harder to ignore. Because by that point, the moon base is no longer just about the moon. It becomes something else entirely, the first serious proving ground for the systems, behaviours, and infrastructure that would one day have to work on Mars. So what is Artemis really trying to build? NASA is saying this much more directly now than it used to. The moon base is not just about the moon, it is meant to be a proving ground for Mars. That is a core part of the logic now. In the 2026 Moonbase Guide, the Mars Forward section ties the lunar outpost directly to future crewed Mars missions. It talks about nuclear technologies, independent operations, human factors, logistics, dust tolerance, planetary protection, and shared systems. That matters because it changes how you should read the whole architecture. Mars is not some extra destination added at the end for excitement. Mars is already shaping the design of the moon base right now. That means every major Artemis problem has two layers. One layer is lunar. Can the system work at the South Pole? Can the crew survive? Can the cargo flow stay alive? Can the site grow without collapsing under its own complexity? But the second layer is the real reason NASA cares so much. Can these same categories of systems work far from Earth, with less help under real operating pressure, in a place that will not forgive weak design? The moon is where NASA wants to find out which ideas are solid, and which ones break before the agency risks a Mars crew with much less margin. That is why nuclear power matters so much. It is not just one more option for keeping a lunar outpost running. It is one of the clearest Mars links in the whole architecture. NASA's lunar power planning and its fission surface power work connect directly to Mars, where fission has already been chosen as the primary power approach because it can keep working even when dust blocks sunlight. That is a huge point. A reactor on the moon is not only there to keep lunar systems alive through darkness and cold, it is also a full-scale rehearsal for a world where solar power has even more serious limits. And once you think about it that way, the importance of lunar nuclear systems gets much bigger. The reactor hardware matters, the deployment methods matter, the shielding strategy matters, the maintenance rules matter, the failure modes matter, the crew procedures matter. Every lesson learned on the moon feeds forward. If something goes wrong on the moon, Earth is still only about 1.2 light seconds away in pure signal time. If something comparable goes wrong on Mars, the delay is much longer and the consequences are much harder to recover from. So the moon becomes the place where NASA can learn how to run nuclear surface power in a real off-world setting while the mistakes are still survivable. The same thing is true for logistics, dust, and local resources. NASA's Mars Forward planning makes that clear too. Long-term habitation on the moon is supposed to develop deep space logistics methods, dust-tolerant systems, planetary protection practices, and resource use strategies that matter for Mars later. That is exactly why the moon matters so much. Mars is farther, slower, and harder, but the categories of pain are already visible on the moon. Abrasive dust, delayed communication, local resource use, crews with more independence, power systems that cannot fail, hardware that has to survive in a hostile environment for a long time. The difference is that the moon gives NASA a much safer place to make mistakes. That is not a small advantage. It is the difference between a bad month and a disaster. On the moon, you can still test whether a dust control method actually works, whether a robot can really keep a site alive, whether local oxygen production is worth the machinery, whether crews can stay effective with more local decision-making, and whether the support architecture can survive real operations. If one part underperforms, the system can still be studied, corrected, and improved with much better odds than on Mars. That is why the moon is not a distraction from Mars. It is the shortest path to finding out which Mars assumptions are real. Then there is another layer people often overlook. The hardware is important, but the standards may end up being almost as important. NASA's Moon Base Guide keeps emphasizing interoperability across government, industry, academia, and international partners. That means things like docking rules, power interfaces, communications protocols, cargo handling standards, servicing methods, and common system assumptions all matter. Those details sound dry until you realize what they do. They determine whether multiple providers can actually work inside the same off-world infrastructure without rebuilding everything from scratch each time. That is a huge part of what turns exploration into a large operating system. If one company's cargo system cannot connect to another company's power system, or one partner's rover cannot use the same communications framework, or visiting assets all require different one-off support rules, then growth stays slow and fragile. But if the moon base creates a real ecosystem where multiple vehicles and multiple organizations can plug into the same support structure, then Artemis will have done something much larger than building a remote outpost. It will have helped define the first serious operating standards for human infrastructure beyond Earth. And standards matter because standards are how frontiers become scalable. Without standards, every mission is custom, every connection is special, every interface is a risk. With standards, more providers can participate, more systems can interoperate, and the architecture can grow faster than any one organization could grow it alone. That may become one of Artemis's biggest legacies. Not just the hardware on the moon, but the rules that let off-world hardware work together. So when you step back and look at the whole picture, the moon base stops looking like a camp or even just a science station. It becomes something much more serious. NASA is trying to find out whether humans can build a self-extending foothold off Earth using shared infrastructure, local resources, autonomous work, durable power, connected surface systems, and crews who can operate with less help from home. That is the real test. Not whether astronauts can touch the surface again. That was proven a long time ago. The real test is whether the system can keep getting more capable instead of resetting after every mission. And if Artemis can do that, then the moon changes meaning completely. It stops being the far edge of the old space age story. It becomes the place where the next phase is trained, stressed, corrected, and made operational. The next crews do not just learn how to land there, they learn how to stay there, use it, build with it, and depend on it without being constantly rescued by Earth. That is why the Artemis moon base matters. Not because it will be the biggest base, or the most comfortable, or the final goal. It matters because it is the first serious attempt to see whether human civilization can extend its working systems off Earth and keep them alive. Shared power, shared logistics, shared comms, local water, local material, robots doing routine labor, crews making harder decisions on site. Those are not just moon mission features, those are the early pieces of a permanent off-world operating model. If NASA can make that work at the lunar South Pole, then Mars stops being only a dream people talk about in future tense. It becomes the next environment where those same hard lessons have to work under even worse conditions. And that means the moon is not the end of the story. It is the place where the next story learns how to survive. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.